11.6 Permutations. In this lesson, we will learn how to use permutations to count possibilities. Permutation just means an arrangement of objects in which order is important. Counting permutations of n objects taken all together. So let's take a look at this example here. What are all the total possible ways to arrange the three letters A, B, and C? Note, you can also use a tree diagram to find all the possible permutations. But here I already listed all the different possible ways. ABC, ACB, BAC, BCA, CAB, and CBA. By the multiplication principle, each time you choose a letter to make a permutation of the letters A, B, and C, the number of remaining letters that can be chosen decreases by 1. The number of permutations would then equal to choices for first letter times the choices for the second letter times the choices for the third letter. So for the first time you pick a letter, it would be 3. And the second time you choose a letter, you will have 1 letter less, so it will be 2. And by the time you get to the third letter, you will have 2 less. And so you have 1, 3, 2, 1, 6 ways. Or we can express this as n factorial. 3 times 2 times 1, 6 ways. And also note that 0 factorial equals to 1. Let's practice. 6 factorial just means 6 times 5 times 4 times 3 times 2 times 1, which equals 720. And 7 factorial is 7 times 6 factorial. You've already calculated 6 factorial here, so you just have to multiply by 7 to 720 to get 5,040. Okay. Doing this is not very interesting. So now I'm going to give you a word problem that involves using factorial or permutation. Posters. You have 4 posters to hang in your room. You want to put 1 poster on each wall. How many ways can you arrange the posters? The word arranged gives you a hint that you must do permutation. Arrange the objects in different ways. So this means order matters. So there's 4 posters and I want them in all different ways. So 4 factorial. 4 times 3 times 2 times 1. 24 ways. Part B. Counting permutations of n objects taken R at a time. Okay? Suppose in a previous poster example, you had 7 posters. And you want to choose 1 poster for each wall. You can use the multiplication principle again to count the number of possible arrangements of the posters. So the number of permutations would equal to the choices for the first wall, which would be 7. And then at the time you want to make a decision for the second wall, you'll have 1 less poster, 6, and then 5 fourth, and so forth. But then you'll only have 4 walls to post your posters, so you stop at 4. And taking the product of all of these numbers would just be 840. And this situation shows the number of permutations of 7 objects taken 4 at a time. So here we have n objects taken R at a time. This is a situation here. So we can also represent this by 7 factorial over 3 factorial. And this above example suggests the following rule. Permutations. Algebra. The number of permutations of n objects taken r at a time can be written as NPR, where NPR equals n factorial over n minus r factorial. So here we have a numerical example of 5p3. So you take 5 factorial, and you take the difference of 5 and 3, which is 2 factorial, and then you would simplify all the way to get 60. So here we have 4 choices, 7p4. So 7 factorial over 7 minus 4 factorial gives you 7 factorial over 3 factorial, and this is where it comes from. So this formula always works for the situation of n objects taken r at a time and when order matters. Okay, let's practice some problems here. 6p2, 6 factorial over 6 minus 2 factorial gives you 6 factorial over 4 factorial. Okay, so 6 times 5 times, I'm going to stop at 4 factorial because it's wasting time if you were to write 4, 3, 2, 1 when you can cancel out 4 factorial. So 6 times 5 would give me 30. And here 5p5 would be 5 factorial over 5 minus 5 factorial. So we have 5 factorial over 0 factorial, and 5 factorial would just be 5, 4, 3, 2, 1. 0 factorial, remember, is 1, so we don't have to write that anymore. But if you want to, I'll write it down for you. 120. And for 8p3, 8 factorial over 8 minus 3 factorial. So 8 factorial over 5 factorial. 8 times 7 times 6 times 5 factorial. Stop there. 5 factorial cancel out. And 876 would be equal to 336. Okay, now that you understand how to calculate a simple permutation problem, now we can apply this formula or this concept into a word problem, which makes this more interesting. Okay, science fair. Judges at a science fair are awarding prizes to first, second, and third place finishers. And in this scenario, order really matters. Okay, so I want to write that down. Order matters. So we need to use permutations. Okay, so the science fair has 10 contestants. How many different ways? Okay, different is also a clue that you have to use the permutation formula because order matters. Okay, so how many different ways can the first, second, and third place prizes be awarded? Okay, so there's only 3 places. 10p3. Okay, so there's 10 contestants in all. You can only have 3 places. And how many different ways can we arrange this? 10 minus 3. So 10 factorial again. 7 factorial. 10, 9, 8. 7 factorial. Stop there because we can cancel this out. So we had 720 ways of arranging the first, second, and third place prizes. Apologize about this. Okay, so I'm going to write 720 here. That's your answer. Finding a probability using permutations. Okay, garage door. Your garage has a keyboard that can be used to open the garage door. The code has 5 digits. Okay, every time you see codes, most likely you have to use permutations because order matters. You remember that 5 digits are 1 through 579, but you cannot remember the sequence, meaning the correct order. What is the probability that you can open the garage on the first try? So let's first calculate the number of permutations. So there's 5, you know the 5 numbers. Okay, so we know it's 5p5 because you're choosing all 5 numbers out of 5. So 5p5 just means 5 factorial. 5 minus 5, 0 factorial, because you could have just written 5 factorial, which is equals to 120. And the probability of getting it correct on the first try will be only one time. So you just write 1 out of 120. Okay, remember, probability just means the possibility of getting it right, the chances of getting it right out of the total number of tries. So there's only one possibility out of 120 tries. Okay, and then here we have the lock. The combination for a lock consists of the numbers 4, 22, and 8. You don't remember the order in which the three numbers are to be entered. Again, order tells you permutations. Find the probability that you open the lock on the first try. So this is a very similar problem. Again, it's 3p3 because you're going to be choosing 3 numbers from, you're going to be choosing 3 numbers from 3 numbers. Okay, so here's 3 factorial, 6 ways. So the probability on first try would just be 1 out of 6. There's only one chance of you getting it right out of 6 possibilities. Okay? Here we have more practice. You have 6 books, but there's only enough space on your bookshelf for only 4 of them. How many different arrangements of the books are possible on your bookshelf? Again, permutations because of the word arrangements. So 6 factorial over 6 minus 4, 2 factorial. 6 times 5 times 4 times 3. Okay, this part you can just cancel. So the product of all of the numbers is just 360. Okay? And next one lists all the permutations of the letters A, B, C, and D. I'm going to make it a little simpler for you. I'm going to take out D. Okay? You could just use a tree diagram so you don't mess up or leave out a possibility. A, B, C. So you can have B, C, C, B, A, C, C, A, C, A, C, B, C, A, B, C, B, A. And these are all the possibilities. Okay, and here's another way of looking at permutations. Write the expression using factorials. Okay, so since you have 30 and 29, you can take 30 factorial. Okay, since there's 2 numbers, I'm just going to do 30 minus 2. The 2 comes from the fact that you have 2 numbers here, and there's the starting number is 30. So 30 factorial over 28 factorial. Okay? And other possible examples of using permutations would come from alarm codes, iPhone passwords, computer passwords. These are situations or scenarios where order matters. And this concludes our lesson.